Hi everyone, welcome to section 10.6, which is not only the last section in module 10, but the last section in this entire course. So in 10.6, we're going to explore some applications that require sine or cosine laws. So when we talk about applications, we're really talking about word problems that are representing some scenario in real life. In order to solve these problems using maybe the sine or cosine law, we need to first draw a sketch. That sketch is going to be critical because it will contain all of the given information and some information that we can decode and insert on those pictures or sketches. So once we have a good sketch of the application or of the problem at hand, we're going to be able to make a good judgment and choose the appropriate formula to use in order to solve these application problems. So one thing I want to just be mindful of is we don't necessarily need to find all missing sides or angles at play. We may only be looking for one specific side in order to solve the problem. So let's take a look at our very first example. So let's have a read with example number 1. It says a ship travels 60 nautical miles due east and then adjusts its course to north 75 degrees east. After traveling 80 nautical miles in that direction, how far is the ship from the point of departure? So sometimes it takes me a couple of attempts to make a really solid sketch. So let's just begin and have our point of departure. So if we have a ship that's traveling 60 nautical miles due east from its point of departure, I'm just going to make our point of origin here. And then in my mind, I'm going to create sort of a north, south, west, east plane. So if we travel due east, what that means is we are going directly to the right, and we're going to do that or travel that direction for 60 nautical miles. So we have 60 nautical miles as a side length given so far, but then we have an adjustment in our direction. So from here, as soon as you see that there's a change in course or a change in direction, I want to give you the hint to sort of map out a new coordinate plane here. So it's almost like we're starting back from the origin again, but we're going to travel north 75 degrees east. So I'm going to drag my pencil north and to the east. So east 75 degrees. So I'm going to drag to the right for a 75 degree angle. This is my new direction of travel. So we can see here that we're creating a second leg on this triangle. Now we travel another 80 nautical miles in that direction, and what they're asking is how far the ship is from its point of departure. So if we draw the third side of this triangle, that's actually what we're after. We're after X here. Now there's some information that we have been given that I haven't quite labeled on this triangle yet. So if we know that we traveled north 75 degrees east, then I know 75 degrees is sitting where I dragged my pen or dragged my pencil. So that's a 75 degree angle, but that's not the angle of the interior of this triangle, because I know that there's a 90 degree angle just to the left of it. So we've created quite an obtuse angle here. So if I know that this is a right angle because I've traveled north 75 degrees east from there, I can add together the 90 degrees with the 75 degrees to get a total of 165 degrees. So if you'd prefer, you can sort of redraw this sketch a little bit rather quickly here. We know that this interior angle now is 165 degrees in total. We still have a side leg of 60 nautical miles, and we have another side leg measuring 80 nautical miles. And what we're looking for is X, so the distance from the point of departure to where that ship has stopped. So there's only one side length missing, and we have to decide whether sine law or cosine law is going to be useful in this case. So this is where we go back to the orientation of the information given. I have two sides, I have one angle, and that angle is sandwiched between those two sides or nestled between those two sides. So this is a side angle side triangle. Because it's a side angle side orientation, I know that I can use the cosine law in order to solve. So with the cosine law, I haven't really labeled anything as A's, B's, or C's, so you can go ahead and do that if you like. So instead of X, you can almost think about that as side length A, which would mean 165 degrees is angle A. And then B and C don't really matter. We could say that angle B is in this far corner and angle C is in our upper corner. We don't need those angle measurements at all. We have enough information to go ahead and use the cosine law. So if we have angle A, the version of the cosine law that we want to use will start with A squared. So we can say A squared is equal to B squared plus C squared minus 2BC multiplied by the cosine of angle A. So A squared, or X squared in this case, is going to be B squared, or 80 squared, plus C squared, or 60 squared, minus 2 times 80 times 60 multiplied by the cosine of angle A, which we know now is 165 degrees. This just becomes an exercise in your calculator. So what we get for an A squared value is 19,272.89 essentially. But remember, that's A squared, so that's the side length squared. We're looking for just A, so the square root of that number is going to be approximately 138.8 nautical miles. So that's the only side length missing, and that's the side length that we just solved for, so the problem or the application has been solved. With most applications, we want you to finish your answer with a proper sentence, so you could say something like, the ship is approximately 138.8 nautical miles from its point of departure. Our next application might take a little bit of practice to be comfortable with the type of picture you're going to be drawing. So here it says the course for a boat race starts at point A and proceeds in the direction south 52 degrees west to point B. From point B, it heads south 40 degrees east to point C and finally heads back to the start. If point C is 8 kilometers directly south of point A, find the distance of the course to the nearest hundredth. So what we need to do is sort of get some of these side measurements and angles sorted. And this is one of those instances where I might take a couple of shots before I actually come up with a picture that I'm happy with. So if we start at point A, and again, I'm going to map out a coordinate plane, or at least a direction, so I can map clearly south 52 degrees west. So again, I'm going to head south, which is just straight down from point A. And then I'm going to swing to the west, which means I'm going to swing to the left. So if I drag my pencil 52 degrees, this is the new direction of travel from point A. And again, we can mark that as 52 degrees because that's the direction we were given, south 52 degrees west. Now from point B, we change direction, and as soon as there's a change in direction, I once again will map out that coordinate plane just to make my life a little bit easier. From point B, we're going to head south 40 degrees east. So again, south, but I'm going to swing my pencil 40 degrees to the east, so 40 degrees to the right. So I'm going to create that angle, and that's my new direction of travel. Now in this particular application, again, let's mark that 40 degrees so that we have all of the information that we can at hand. So if that little wedge is 40 degrees, we've been told that point C lies 8 kilometers directly south of point A. So if I go back to point A and I draw a line, that line ultimately will connect with point C. So I might have overshot that line just a little bit, but that's okay. We can erase that extra little tab here. Let's just fix this line. There we go. So this is our picture. We've got 8 kilometers in terms of length due south when we measure from A to C. So when I start looking at some of the angles in this triangle, I definitely know that 52 degrees is an interior angle of the triangle, but I'm missing a lot of other information. So we're going to start decoding the rest of that information using properties of angles that we know from before. If we know that 40 degrees is the angle wedged between that south line and our direction of travel, then what I know is inside this portion must be 50 degrees because those two angles together are going to measure 90 degrees. But that's not the entire interior angle of this triangle. We're actually going to use some other properties of things like alternate interior angles to get some more inside measures from this triangle. So if we can extend or imagine that the parallel lines, the west-east lines, are parallel to one another, we have what's called a transversal. So if I continue those lines 52 degrees, we'll have an alternate interior angle that's equivalent. So if we know 50 degrees is mapped here in angle A, we also know that 52 degrees is going to be mapped here outside of the triangle. So if that measures 52 degrees, I can use that information to get the remaining segment of that 90-degree angle inside the triangle. So if that's 52 degrees, this angle here must measure 38 degrees. So just to reiterate how we got that 52-degree angle to help us find other angles inside that triangle, if we had a set of parallel lines, and we'll call those parallel lines, or maybe north-south lines in this case. If we have a set of parallel lines, so the north-south lines, and we have a transversal that runs through it, if we were given 52 degrees as the angle inside at point A, then we know 52 degrees is alternate interior to that as well. So this must be 52 degrees. So if I were to add up 52 degrees and I knew there was a 90-degree angle on the inside, then 52 degrees plus this unknown must sum to give me 90 degrees because that's a right angle. So that's how we're getting 38 degrees as another part of that interior for angle B. Now, it's easier for us to sort of redraw this because this sketch looks a little bit messy and it's hard for us to decode some of that information. So if I were to redraw my sketch now, we have still points A, B, and C. But if I were to clean up the information that we're given, then we still have point A at the top, which is a 52-degree interior angle. We have 50 plus 38 or 88 degrees sitting at angle B. And angle C is unknown, but we could find it if we really wanted to or needed to, because we know that all three angles would sum to give us 180 degrees. So the only side length we were given in this case is 8 kilometers, and that stretches from point A to point C. So if we want to do a quick calculation here for for angle C, because that's the only unknown angle that we have right now, if you were to take 180 degrees, subtract the 52 degrees from angle A, and then subtract the 88 degrees that were given for or found for angle B, we know that angle C measures 40. Whoopsie. There we go, 40 degrees for angle C. So if we go back to find out what they're actually asking us for, they're saying find the distance of the course to the nearest hundredth. So the course needs to travel from point A to B, from point B to C, and then back to point A. So that's sort of the loop that's happening with this race. What that means is we're missing two side lengths. We need to find side C and we need to find side A. So if we take a look at the information we're given, we have all of the angles and we have one side length. So essentially we have an angle side angle triangle, or we could say it's an angle angle side triangle. Either way, we know that for an ASA triangle, this is a cosine law problem. So the cosine law, just as a reminder, is A over sine A, which is equivalent to B divided by sine B, which is equivalent to C over sine C, and we can use 2 out of any 3 of these parts to solve. So let's solve alphabetically. We'll solve for part A first. If we're solving for side length A, then we'll use A over sine A, of course, for the formula. And for given information, we know side length B and we know angle B. So we must use B over sine B as well in this formula to solve. So A is unknown, we can leave it as such, divided by the sine of angle A, so the sine of 52 degrees, and that's going to be equal to B, or 8 kilometers, divided by the sine of angle B, or the sine of 88 degrees. Once again, we're going to cross multiply and divide. If you want to write that out in one step, you're welcome to, because what we're trying to solve for here is that numerator, that side length. So we can multiply 8 by the sine of 52 degrees, so we'll cross multiply, and then we can divide by the sine of 88 degrees. So just be careful with your calculator that you've got clearly 8 times the sine of 52. Check your mode, make sure you're in degree mode. So 8 times the sine of 52, get your answer, and then divide that by the sine of 88. And what that will give you is 6.3. So A is approximately 6.3 kilometers. So we've got a second side length here. We know it's 6.3, and we're ready to solve for the third side. So to solve for that third side using sine law, we can still use B over sine B as your given information. But what we're trying to do is find C, or side length C, so we must use C over sine C as the second part of our sine law. So we'll have 8 divided by the sine of 88 degrees, equivalent to side C, which is an unknown, divided by the sine of angle C, or 40 degrees. So once again, to get C isolated, we're going to take 8, multiply that by the sine of 40 degrees, and then divide by the sine of 88 degrees. So again, be careful when you cross multiply and divide. 8 times the sine of 40 degrees is now divided by the sine of 88 degrees. So you should have 5.1 approximately when you find the measure for C. So you've got another 5.1 kilometers added to this loop. So if I fill that in on my diagram, we have 5.1 rather kilometers for side C. We have 8 kilometers between A and C, so that's the last leg of the journey, plus we have 6.3 kilometers between points B and C. So if we add all of those together, we have a total distance measuring 19.4 kilometers. So if we start at point A and work our way back all the way around to point A, we'll have a total distance of 19.4 kilometers. Once again, because this is an application, you need to state your answer in a very clear, well-defined sentence. Let's give a read to our third application. It says points A and B are on opposite sides of a pond. Point C is 50 meters from point A. A surveyor determines that the angle A is 112 degrees and angle C measures 42 degrees. What is the width of the pond to the nearest meter? So if we can imagine, here's our pond. We have 2 points on opposite sides of the pond, and we know those points are A and point B. So we can draw one leg of our triangle connecting those 2 points across the pond. Now there's another point, and that point C is measured 50 meters away from point A. What I don't know right now is where to locate that point C. So let's read a little bit further to see if we can gather some more information. A surveyor determines that the angle measured for A is actually 112 degrees. So what you need to do is actually make an obtuse angle for angle A. So if I make an obtuse angle for angle A, it puts me sort of outside of that pond, because again, the surveyor is measuring that angle for us. So let me highlight in pink. The surveyor is telling us that angle A is measuring 112 degrees. So we know that point C is sitting somewhere outside of the pond, and we would say, or in this case, the way I've drawn it, we also know that point C is actually 50 meters from point A. So we have one side length and we have one angle sorted so far. Now we can connect the dots on our triangle And we're also given a little bit more information. It says angle C measures 42 degrees. So we can put 42 degrees inside this triangle as well. What we see very clearly is we have two angles and we have the side length between them. So we actually have an angle side angle orientation. So because this is angle side angle, we know this is going to be sine law. So what it's asking us is to find the width of the pond to the nearest meter. So what they're asking us to find is the distance across the pond between A and point B. So this is going to be lowercase c. That's the side length that we're after. So in this case, when we use sine law, we need to have an angle and side opposite in terms of a pairing in order to get that sine law started. So I can see two of the angles labeled very clearly. The third angle is very quick for us to find. So if we take 180 degrees and we subtract 112 degrees and we subtract 42 degrees, we have 26 degrees remaining inside that angle for angle B. So the points or the parts of our sine law that we can use in this case are going to include, of course, c over sine c, because c is what we're trying to solve for, and b over sine b, because we have both side length b and angle B. So now we can just plug in the important pieces of information. So c divided by the sine of 42 degrees is going to be equivalent to side length b, or 50 meters, divided by the sine of angle B, which we know to be 26 degrees. So once again, we can cross multiply and divide. So we'll have 50 multiplied by the sine of 42 degrees, and we're going to divide that by the sine of 26 degrees. So you can get an approximation for the width of the pond using that formula. So once again, 50 times the sine of 42 is now going to be divided by the sine of 26 degrees. So we've got 76.3 meters when you round to the nearest tenth. So once again, because this is an application problem, you should have a final statement that reads something like, the width of the pond would measure approximately 76.3 meters. So let's give our last application a quick read. Two fire towers, A and B, are 18.5 kilometers apart. The bearing from A to B is north 65 degrees east. A fire is spotted by a ranger in each tower, and its bearing from Tower A is north 28 degrees east, and from Tower B is north 16.5 degrees west. Find the distance of the fire from each tower. So this is a lot of information, and we have to be very careful with our sketch. So I need to first travel from point A to point B. So I know they're 18.5 kilometers apart, but I need to know how to draw them in terms of their positioning compared from one to the other. So if I have point A here and I travel north 65 degrees east, so I'm going to travel upwards, north, and then drag my pencil 65 degrees to the east. That's the direction that's going to get me to point B, or Tower B. So we want to make sure we include that 65 degrees as the angle that we've swung here on the outside of that line. And we want to mark Tower B very clearly. So we know that that line is measuring 18.5 kilometers, and we can label that in just a moment. Now we're also told that both towers spot the same fire. So the fire is at a bearing of north 28 degrees east from Tower A. So if we go back to Tower A and we want to draw where that fire is, I'm going to do this in a different color. I have north, so I'm going to head north or straight up, and then I'm going to drag my pencil only 28 degrees to the east. So it's going to be a slightly smaller angle, and this is going to be the direction of sight for that fire. I don't know how far away that fire is. That's kind of part of the problem. But what I can do now is mark this angle as 28 degrees. So we have two angles that are maybe going to help us find some interior angles for this triangle. Now from Tower B, the fire measures north 16.5 degrees west. So again, I'm going to measure from Tower B to the fire northwest. So that means north is upwards, but I'm only going to drag my pencil 16.5 degrees to the west. So that's a slightly smaller angle. So this angle is going to help us figure out where that fire is actually sitting. So we've got the fire sitting up here somewhere. But again, I want to make sure I measure that 16.5 degree angle that I just created when drawing out those bearings. I definitely want to redraw this triangle so that we can make sure that our labels are super clear. We're going to have a little bit of work to do to find some of those missing angles, but we'll get to that in just a moment. So if we've got point A or tower A, we've got tower B, and then we've got the fire. We're going to call the fire just C for now. What we know for distance or length is that A and B are 18.5 kilometers apart. Those towers are measuring 18.5 kilometers. Now the hard work comes for finding some of these missing angle measurements. So in order to find some of these missing angle measurements, we have to do a little bit of detective work. And I'm going to start with angle A here. Now, originally we were given 65 degrees measuring from the north line to that direction between A and B, or that line of sight between A and B. But we're also given an outside angle of 28 degrees. So if we subtract 28 degrees from 65 degrees, it's going to be the size of that little wedge inside the triangle. So 65 minus 28 is going to give us 37 degrees. So the interior angle of that triangle is only measuring 37 degrees. So we've got one angle sorted. We can find our last angle now. So there's a lot of information sort of at point B that we can use to find those missing measurements as well. So to start off with, I know I've got 16.5 sitting outside the triangle, but if I want to sum to 90 degrees or make a 90-degree angle, I can take 90 and subtract that 16.5 degrees to get 73.5 degrees inside. But that's not the entire angle here. This is only the wedge that I'm showing inside that triangle. So the wedge between that line of sight between the fire and, let's say, point B and the west line is 63.5 degrees. So I need to find out that other little segment in order to find that interior angle B. What we can do once again is use that notion of alternate interior angles. If I have these north-south lines as parallel lines, then I know that 65 degrees sitting on the top side is alternate interior to 65 degrees sitting on the outside here. So if I take the difference between 90 and 65, because that makes a right angle, I have 25 degrees measured on that inside segment, because I can see clearly that 25 and 65 gives me a total of 90. So angle B is actually made up of two different components. It's 25 degrees plus another 73.5 to give us 98.5 degrees inside total. So what we have now are two angles and a side between them. So this is an ASA triangle. ASA triangles can be solved using the sine law. So go back to the question at hand. It says find the distance of the fire from each tower. So I'm actually looking for B, which would be the distance between the fire and tower A, and I'm actually looking for A as well, which would be the distance between the fire and tower B. So if we do this alphabetically, of course, we have A divided by sine A, and that's going to be equivalent to the given side length that we have, so that's a C measurement, divided by the sine of angle C. Now, before we get worried that we don't actually have angle C, we do if we subtract the other two angles from 180 degrees. So if we take 180 and we subtract 98.5 and we subtract 37 degrees, you get 44.5 for angle C. So we can use that measurement throughout our formula. So A divided by the sine of angle A, which we know is 37 degrees, is equivalent to C, or 18.5 kilometers, divided by the sine of angle C, or 44.5 degrees. Again, this just becomes cross multiply and divide. So we'll have 18.5 multiplied by the sine of 37 degrees, and we'll divide that when we're done by the sine of 44.5 degrees. So that's going to give us side length A, which would measure the distance between the fire and tower B. So just be careful. 18.5 times the sine of 37 is now divided, so be careful with your brackets, by the sine of 44.5 degrees. What you should come up with is roughly 15.9. So we've got 15.9 kilometers between the fire and tower B. The last side length we want to find is side length B, so of course we'll use B over sine B as part of our sine law, and that's going to be equivalent to C over sine C, because that's information that we were given. So B is going to be divided by the sine of 98.5 degrees, and that's going to be equivalent to C, or 18.5, divided by the sine of angle C, which we know is 44.5 degrees. So once again, to solve for B, we have 18.5 multiplied by the sine of 98.5 degrees. That's all divided by the sine of 44.5 degrees. So just one more calculation to go before we have your final answer. So 18.5 times the sine of 98.5, close the bracket, divide that answer by the sine of 44.5, and you get a final answer of 26.1. So 26.1 kilometers is the distance between the fire and tower A. So once again, pull all of this information together in a nice statement. So the fire is approximately 15.9 kilometers from tower B, and it's approximately 26.1 kilometers from tower A. So sometimes the information that you need to utilize in order to solve bits and pieces of these triangles require a little bit of angle manipulation, just like we had in this application. So make sure you have a look at these homework questions and practice finding some of those missing angles. So the homework questions we've chosen here are very specific, so please practice numbers 3 through 5, 7, 11, and 14. And again, this is just practice using sine and cosine laws. So as always, if you have any questions as you go through these applications, or you're not sure where some of these angles are coming from, please make sure you reach out and get some assistance.